Okay, so can you mainly on your screen see the board? Can somebody just type in a chat? Just make sure. Perfect. Okay, so we got f of x equals x to the square root of x power, and we want to find f prime at x. Okay, so the problem is this is x to a function. It's not just x to a power, so the power rule doesn't really work here. So what we have to do is we have to rewrite f of x. So we rewrite f of x, we can rewrite it as e to the natural log of that thing. So e to the natural log of x to the root x power, we can do that. And then what I can do is I can drop that root x down in front. And so this is equivalent to e to the square root of x times the natural log of x. And now to take the derivative of this, of course, the derivative of e to the x is e to the x, right? But the derivative of e to some function power is going to be e to that function and then times the derivative of the exponent. So this is going to be e to the x natural log x and then times the derivative of the exponent. So now the derivative of the exponent, that's actually a product, right? So we got to use the product rule. So we're going to use first times the derivative of the second. So it'll be square root of x times the derivative of natural log x is 1 over x plus the second one, which is natural log of x, times the derivative of the first one. Well, instead of square root of x, that's x to the 1/2 power. So it's going to be 1/2 x to the minus 1/2 power. And then we've got some cleanup and try and make this look a little bit better. So this is going to be e to the square root of x natural log x, and then in parentheses times what? Well, this is going to be, I'm just going to rewrite that as square root of x over x is 1 over the square root of x, or that's x to the 1/2 divided by x to the first is 1 over x to the 1/2 or x to the minus 1/2, either way. Anyway, so it's 1 over square root of x, and then plus the natural log of x over 2 times the square root of x. So I'm going to drop that x to the 1/2 down to the denominator, make it positive, so we have this. So that's what we have in parentheses there. Potentially, I could take a 1 over the square root of x out in front. I don't really need to do that, but what I would like to do is try and rewrite e to the x square root of x natural log x. I had that up here, and of course, we had that as rewrote that as e to the natural log of, I could put that exponent back up there, and then e to the ln undoes it. So this is just nothing more than x to the square root of x power, and then times what's in red there, right? So times 1 over square root of x plus natural log of x over 2 square root of x. So this is probably good enough for your final answer. Once again, product there. We could try and do all kinds of simplification, but as far as a test is concerned, things of that nature, that's what we want. Now, this is an odd exercise, so we should be able to look in the back of the book to see if they have anything like that or if they did some additional simplification. So doing that, usually I have somebody do that for me, but I don't have you in class right now. So let's look at number 15. So they have x to the square root of x minus 1/2 and the exponent times quantity 1 plus 1/2 ln x. So they actually did do that. They they rewrote the red part here as they pulled a 1 over x out here. So just this part, they pulled a 1 over the square root of x out front, and then they're going to have 1 plus natural log of x divided by 2, which is the same as 1/2 times natural log of x. And then what they did is they multiplied the 1 over the square root of x times x to the square root of x. So really they rewrote it as x square root of x divided by x to the 1/2 power because 1 over the square root of x is x to the 1/2. So that's what they did with the green, and then part there, and then they have 1 plus natural log of x over 2. So this is equivalent, but of course we can use, you know, x to the m divided by x to the n power is x to the m minus n power. So they're just rewriting this as x to the square root of x minus 1/2 power times what's left is 1 plus 1/2 natural log x, if you want to write it exactly like the book had it. So this is the book answer. The book answer is correct. Mine was really good enough as well. This isn't necessarily any easier on the eyes. The green one isn't compared to what we had before. So anyway, the trick here is to rewrite this as that's x to a function. So how do we rewrite it? E to the natural log of that thing, and then we can work with it and use derivative theorems that we know. Okay, so hopefully that one's good. Any questions on this one before I erase, because I don't have a lot of board space. Hopefully you can see. I can't really manipulate this right now where I can see my big board. So can you see all the way over to my hand? Looks like you can. So looks like you should be able to see everything that I put up on the board. Okay, so we got that one done. So that was number 15. I'm going to jump to the miscellaneous exercises. And let's look at those. And that is, I'm not sure what page that is, but at the end of the chapter. Number 11. What do we mean by logarithmic definition or logarithmic differentiation? Make up an example. Logarithmic differentiation is just basically taking something and taking the natural log of both sides, taking the absolute value of both sides, then taking the natural log of both sides, and then taking the derivative. And using log rules, though, would make life a lot easier. So if you have kind of a complex fraction, that would be a good time on using logarithmic definition. So when you have a function of x in the numerator, function of x in the denominator, maybe a product or a root, some of that nature, we can use logarithmic differentiation instead of the hard way. So you can just go back. Examples of that are just like the ones that we did in that section. Logarithmic differentiation, I guess I'd want to make sure that you can do it, but it's a process that's going to help you take a derivative of a more complex looking function. So anyway, let's see. What's next one that you wanted to look at there was number 42, I think. 42, what's that say? State the formula given the derivatives of the inverse sine and inverse cosine functions.
Miscellaneous are on the next page so I wanted the miscellaneous on the next page.
Oh, I got you. So you actually had a problem.
Yeah.
Okay, so take the derivative and simplify. 15, do you want part A and B or just part?
I want number 42.
Okay, somebody had number 15. No, wait, no, somebody had number 11. Find f inverse prime. Well, let's start with number 11. So this is number 11 on page 528. Thank you for clarifying that. So page 528, number 11, we've got 8x cubed plus 6x. 8x cubed plus 6x. And we want to find f inverse prime evaluated at D, where D equals 4. Okay, so D is the output. So what did we have on this? We looked at one like this before. So certainly we said, hey, if we know that f is continuous, which we know it's continuous, why? Because it's a polynomial. right? It's also what kind of polynomial is it? It's like an x cubed, so it's gonna go uphill left to right. You know, actually, if you plug in 0, you get 0. So it's gonna look something like this, but we could actually verify that this is increasing. The question is, how could we verify that it's increasing? What's f prime at x? So we could, this is back in Calc 1 stuff, because it is possible that it goes up and comes back down and then goes up again, right? There could potentially be 3 roots on this. But if I factored out a 2x, and that's where the x is 0, so we know that's a root on there, what am I left with? I'm going to be left with 4x squared plus 3. And 4x squared plus 3 can never equal 0. So I'm never going to hit the x-axis again. The other thing that we could do is we could say, what's f prime at x? F prime at x is going to be 24x squared plus 6, right? Which is 6 times the quantity 4x squared plus 1. This does not factor. So basically, the sign of f prime doesn't change. There are no critical numbers here. So since there are no critical numbers, basically, it's going to be either increasing or decreasing for all real numbers. So when we have our interval negative infinity to infinity, we can have the sign of f prime. So if I want test x, I could try x equals 0. And then the sign of f prime is how we did that back in Calc 1. Well, if I plug in 0 into f prime, I get a positive number, which our conclusion for f on that interval, which is actually all real numbers, is that f, conclusion for f is that f is increasing. So we have continuity and we have monotonicity on all real numbers, and certainly on any closed interval containing 4. So then we can use our theorem. The theorem said that if you have continuity and monotonicity on the closed interval, then we could say that f inverse prime evaluated at D is 1 over f prime at C, where f of C is the input, equals D. Okay, so we have to figure out what C is. So f of C, what's f of C? F of C is going to be 8c cubed plus 6c, and that's going to equal D, which is 4. Okay, so you're probably wondering, how do you solve this? Okay, so this is where we have to get into like P over Q tests and stuff like that. You could plug that into a graphing calculator, use a trace function to see, you know, what C is approximately, gives you 0, things of that nature, and then plug it into f prime, which is right here. So I'm not going to do that because I'm not going to make you do that because I don't give you a graphing calculator on your test. So don't worry about that, but that's how you would do that. Okay, does that help? Was that your concern that you weren't able to solve for C? Anybody? Whose was that? Yeah, that helps. Okay, good. Perfect. All right, so don't worry about that. You know, if I had something nicer, but we do need monotonicity. So you either need to know what the graph looks like, or in this case, not sure if it just goes uphill or whatnot, we can go back to Calc 1 methods here to verify it. But you can use, the biggest thing is that theorem at f inverse prime evaluated at D, which is D is the output of the function at C, is 1 over f prime at C. Okay. All right, and I did do one like that, so I focused more on ones that we had to do in class, and then I did 2 of them. I did one where we could actually go ahead and find the inverse. In this case, it's going to be awfully difficult to find the inverse as well, but to find that C that fits that, we would probably want to be using our trace function. Actually, the function kind of looked like this, right? And when I'm out at, 4 is the output. The question is what's the input? We would just trace it up here and get what C is, because f of C equals 4. So we could estimate it. You wouldn't even have to do a trace function. I mean, if you plugged in, what was f of 1? F of x was 8x cubed plus 6x, right? If I plug in 1, I get 14, right? Well, that's too big. If I plug in 2, it's going to be even bigger. So basically, I got to be between 0 and 1. Well, what's f of 0? F of 0 is 0, right? But I want to hit an output of 4. So 1 is over here. That gets me up to like 14. 0 is at 0. So I got to be somewhere in between. So we could keep narrowing it down, plug in a half, things like that, plug in 4/10, so we can get to the nearest tenth without a graphing calculator also. But I'm not going to do this to you on a test, and hopefully not on homework to turn in either. Okay. And then 42 was also in the miscellaneous exercises. Evaluate the indefinite integral. All right. Well, let's check this out. The indefinite integral of dy over 9e to the y plus e to the minus y. Okay. Well, so we need to try and rewrite this if possible. I guess. What did you try on this? Was it Sammy? Was this yours?
Yeah. I tried moving EY to the top by like, since it's like a negative Y, and I tried setting it equal to U, but I just couldn't figure it out.
That didn't really help.
No.
I don't see that. So you can't move the e to the minus y up to the top because you have a plus sign there. So you can't do that. We could like let u equal e to the y, but then du equals e to the y dy, and that doesn't get rid of anything up there. If I factor out, what I might be able to do is I might be able to factor something out. We need to try and make it look like an antiderivative that we have. What if I factored out an e to the minus y out front? What would be left? Well, I'd be left with plus 1 on the right side, wouldn't I? Which is a little bit nicer. And then what would I have in here? I'd still have a 9, but e to the minus y times what is e to the y? Well, you add exponents, so it'd be e to the 2y, right? Because 2y minus y is just y. Now what we could do is we could write this as something kind of perfect square. So let's do that. I don't know, I'm just going off the cuff here. See if we can make it look like anything that we like. So 9 is 3 quantity squared, and e to the 2y is e to the y quantity squared, right? And then plus 1 squared. We have something of that nature. So that's looking a little bit better, right? So now could I let, and by the way, what can I do with that e to the minus y? Could I move it up? I can move it up, so that'd be e to the y dy. So I think this is going to give us a form that now we might be able to do substitution in. So if I've got e to the y dy over 3e to the y quantity squared plus 1 squared, right? Or plus 1. This kind of looks like something that we might actually actually be able to do something with. So if I let u equal 3e to the y, then what's du equal? 3e to the y dy, right? And then so du over 3 actually equals e to the y dy. So this would be equivalent to 1/3. Instead of the integral of e to the y dy, I'm going to replace that with du. Of course, du over 3, right? So the 1/3, I already got the over 3. I pulled that 1/3 out front. And then on the bottom, this becomes u squared plus 1 squared, right? Or 1 squared, right? And that looks like a derivative that we should know, doesn't it? Which one is that?
Tan, right? Tangent.
Huh?
Is it tangent? Inverse of tangent?
Inverse tangent? I believe so. Yep. Yeah, it's just inverse. Yeah. In this case, a is 1 here. So this is, anyway, this is 1/3 arctangent of u and then plus c, right? And then you just back substitute. So with back substitution, instead of u, what was u? U was 3e to the y. So this is going to be 1/3 arctangent of the quantity 3e to the y and then plus c. That should be the answer. Do you have the answers to the even ones or not?
No.
No, so you were just trying it for fun?
Yeah.
That's cool. I like your positive energy. Let me see if I got the answer for it. So believe it or not, I did not look any of this stuff up before jumping on to help you. But this black 1/3 arctangent 3e to the y plus c. Of course, I could verify that by taking the derivative of that, right? But that is the correct answer according to the author. So that's good. So the key here was if you try and use substitution right away, it doesn't really make it look any better. But trying to make it look like something, and the reason that I thought about pulling the e to the y, first of all, it's a trick. It's an algebra trick, but it's one that I've seen before, so that helped me. But I saw that 9, and hey, that's like 3 squared, right? And so how do I make the e to the y power, like something squared? Well, if I pull an e to the minus y out, that's e to the 2y left in there. And then I can rewrite that as something quantity squared. And then, I've got the plus 1, but I can take that e to the minus y because it's multiplication. I can take that e to the minus y and pop it up top. So that was the trick there. And then I could just use regular substitution by letting u equal 3e to the y. So it's just u squared plus 1 squared. And then that arctangent formula, antiderivative formula that yields arctangent of u came into play. Okay, so hopefully that helps. So that's kind of what you want to do on some of the awkward ones. All right, anything else? 5, 6. I don't know if I'm going to look at it quick. I don't know if I want to go through. Number 17. Yeah. I've given you enough. Just focus on the word problems that you either had to do to turn in or the odds that we, or the ones that we did together. And then I had some extra ones in video too. So I'm not gonna go through that right now because we could do word problems all day, but I still want to eat supper tonight yet. And since it's 9:30, I'll probably skip that one for now. Any questions on anything else for me? No? Somebody asked me, not everybody was on, but somebody asked me if there are any inverse trig formulas that are going to be given to you, and the answer is no. So the only thing that's on that trig sheet is just like basic trig stuff, you know, double angle formula and sine of 2u, cosine of 2u, you know, stuff like that. Anyway, so you need to know the inverse trig stuff. And then derivative cosh is sech, or sinh, derivative sinh is cosh, you know, that is stuff like that. So the hyperbolic trig stuff. Any other questions on the hyperbolic trig? And then, you know, just derivative of, you know, logarithmic differentiation, definitely need to know that too. Do you want to, I don't know, and then power rule, like the integral of, like, a to the nx or whatever, or 2, you know, the integral of 2 to the x power, stuff like that. Remember that? That was early on. I think that's section 5.5. Oh, it might have been before that too. But anyway, there's a couple different ways to write it, but I will write this down. If I want the derivative with respect to x of log base a of x, I mean, you need to know this. This is 1 over x natural log of a, right? So if you want to know that, that'd be great. So a lot of these formulas, you know, there was a lot of formulas, but how could I rewrite log base a of x? I could rewrite that as the natural log of x over the natural log of a, right? And natural log of a is a constant, so that's just a number. So if I want the derivative with respect to x, this would be like natural log of x over, you know, 5 or something like that. You can pull that constant out in front, which is 1 over natural log of a, and then take the derivative of the natural log of x, which is just 1 over x, right? Well, that gives you 1 over x natural log of a. So this isn't rocket science to have the derivative of log base a of x to be 1 over x natural log of a. But instead of reproving it every time, if you just know the formula, then that's certainly gonna help you. Okay. Anything else? Any other awkward ones that, here, another theorem. Derivative with respect to x of a to the x power. So this is like, you know, 5 to the x power or 2 to the x power or pi to the x power. Anyway, it's that. So it's, you know, what's the derivative of e to the x is e to the x, right? So it's kind of like that. Derivative of a to the x is a to the x, but it's not an e, so times natural log of a. The natural log, if it was e to the x here, if I wanted derivative with respect to e to the x, with respect to x of e to the x, I mean, well, you could use the same formula that's in black above it. Well, that's e to the x times the natural log of e. But what is the natural log of e? That's just 1, right? They undo each other, which is just e to the x. Derivative of e to the x is e to the x. Okay, so these are a couple formulas here, these theorems. These are a couple of formulas that you're going to want to know coming into the test, if you don't already. Hopefully you already do. All right. Any other? And then, of course, we had the ones on the sideboard too, right? Inverse trig stuff, you know, whatnot. But let me just do a couple. Huh?
Also couldn't figure out number 40 for the miscellaneous. It's like the a to the x. It's like one of those.
Okay, so let's do that first, and then maybe I'll come back to inverse trig. Evaluate the indefinite integral. That one, number 40.
Yeah.
Alright. It's 40 on page 528 still. And we want the integral of 10 to the x power plus 1 all over 10 to the x power minus 1 with respect to x. Well, I don't know. I mean, we could try some different stuff. I don't see like perfect square stuff going on. This is like a plus 1 over a minus 1. We could try substitution. If we let u equal 10 to the x power minus 1, then what would du equal? The derivative of a to the x power is a to the x power, 10 to the x, times the natural log of 10, right? Times natural log of a. And then the derivative of minus 1 is 0, right? So anyway, this would be, it would just be 10 to the x, natural log of 10 dx. So, you know, natural log of 10 is just a constant, right? So I could get rid of that and say that du over the natural log of 10 equals 10 to the x dx. Now the question is, do I have 10 to the x dx on top? I have one, but then I have a plus 1 there. So does anybody know a basic math trick that I could maybe do? If I got a plus b all over a denominator, so let's call that purple denominator c. So this is a plus b all over c. Couldn't I rewrite it as a over c plus b over c? Yeah, I think that might work. So couldn't I rewrite this as the integral of 10 to the x power over 10 to the x minus 1 dx plus the integral of 1 over 10 to the x minus 1 dx. So I could split this up into two parts up here. Now the purple one actually works then, my purple substitution. If I let u be the denominator, okay, what does this left one become? This becomes the integral of u is on the bottom, and then 10 to the x dx is replaced with what? Du, and then times 1 over natural log of 10 out front. So what's the integral of 1 over u? That'd be the natural log of the absolute value of u, right? And then plus c. But anyway, times 1 over natural log of 10. Substitute back in what the natural log is. So it's 1 over natural log of 10 times the natural log of the absolute value of 10 to the x minus 1. So that's the left one. That's this one. That was in purple. By the way, natural log of 10, how could I rewrite natural? So if I got 1 over the natural log of 10, how could I rewrite that? Natural log of 10, let's see. Can I put, this is log base e of 10, right? Is the natural log of 10 is, natural log is log base e. So couldn't I rewrite that as 1 over log base 10 of 10 over log base 10 of e, which log base 10 of 10 is 1, right? So this is equivalent to just log base 10 of e. So instead of 1 over natural log of 10, I could rewrite that as log base 10 of e, log of e, which is probably what the book would have for that part. And then I would have to take the derivative of the right side as well. The right side really doesn't look as nice, but I could do this and get a 10x, 10 to the x in there, and then do some substitution, stuff like that. So it looks a little awkward, but basically this is what I would see you would have to do with that, and then keep going. So for the sake of you studying what is really important to do instead of just trying to figure out one particular messy problem, I'm probably gonna let that one go at this. But it's a great question. So ultimately I'm just gonna see if I can look this up. What number was that, 40? Yeah. Oh. They used a much different algebra trick, but they did get the left side of what I got in there, but they used some other awkward algebra trick. So we're just gonna let that one go. Anyway, okay. So I think we would probably end up with something equivalent. So I don't know. They wrote that as 10 to the x over 2 times 10 to the x over 2 plus 10 to the minus x over 2 is how they did it. So I'll tell you what they rewrote the top as. 10 to the they pulled out a 10 to the minus x over, or 10 to the positive x over 2 times 10 to the positive x over 2 is 10 to the x. Whoops, and then plus 10 to the minus x over 2, because when you multiply these two together, you just get 1. Anyway, and then they do the same thing on the bottom and rewrite that as 10 to the x over 2 times 10 to the x over 2 minus 10 to the minus x over 2. So this is what they did. Then the 10 to the x over 2's cancel, and then they have this on top divided by that on the bottom. I don't see that that's any prettier, and I like my way of doing it a lot better. So anyway, so we'll just let that one go. All right. Any other questions? You want some inverse tricks? I got about, I don't know, 5, 10, 15 minutes, 15 tops. All good with inverse trig derivatives and antiderivatives, stuff like that? Hopefully. Where's that? What's the derivative with respect to x of arc sine x? You want to know that, right? So it's 1 over square root of 1 minus x squared, right? Well, what if that's a function? So what if I have the derivative with respect to x of arc sine of x squared plus 2? Well, I'm going to act like it's okay, and it's 1 over the square root of 1 minus that thing quantity squared, but then times the derivative of what's inside by the chain rule, right? So times 2x. So I can put that 2x on top, right? That makes sense? If you wanted to square that out, you can. It doesn't really, you don't have to for me, right? So this is good enough for me. So the derivative of arc sine is 1 over square root of 1 minus x squared. Derivative of arc cosine is what? It's minus 1, very similar, minus 1 over the square root of 1 minus x squared. Once again, if that's and x squared plus 2, that'd be x squared plus 2 minus that quantity. What did I do wrong? Oh, yeah. So it's basically the same thing, except I'd have a minus sign on top, right? Because this is the only thing that's different in the formula. But if you have a function of x times the derivative of what's inside by the chain rule. And then, what else do you need to know? Derivative of arctangent. Need that one too. We used this one before, I think. Or we use the antiderivative formula for it. Derivative of arctangent is 1 over x squared plus 1, right? Once again, if that's a function like x squared plus 2, that'd be x squared plus 2 quantity squared, and then times derivative of what's inside, so times 2x. And then you could see if anything cancels. Okay? And then we had the 3 formulas that were on the sideboard, right? By the shock face gal, right? So you had those 2. We had 3 of those. We also have derivative of arc secant. And so this is 1 over x square root of x squared minus 1. Once again, if that's a function times the derivative of the function, you just plug in that function in everywhere you see an x, right? Stuff like that. So just make sure you know those. What was derivative of arc cotangent? Derivative with respect to x. Arc cotangent of x. Okay, so what was cotangent? What was arc tangent? It was 1 over x squared plus 1. So what's arc cotangent derivative is minus 1. So the only difference on that one is the minus 1. And then we have one more then, the derivative of arc cosecant x. Okay, what's the derivative of secant? Is this one. So exact mirror image of that, except what? We have a minus because there's co there. So minus there. So if you know derivative of arc secant, you should know the derivative of arc cosecant. If you know the derivative of arc tangent, you should know the derivative of arc cotangent because you just attach a minus 1. If you know the derivative of arc sine, you should know the derivative of arc cosine. Okay, so 6 major ones there. And then the antiderivative, similar, but you do have the 1 over a stuff there to pay attention to. When you don't just have a 1, so I'll just review those real quick too, and then I'll be about out of time. But if I have the antiderivative with respect to x of square root of a squared minus u squared, x squared, I'm using an x here, a squared minus x squared, x is a variable, a is a constant, okay, then this is going to equal the arc sine of x over a plus c, okay? So there's no 1 over a in front of this. So for example, if I had the antiderivative with respect to x of the square root of 9 minus x squared, this is going to be the arc sine of x over 3 plus c, right? Pretty simple deal. And then just, you know, if you have a function of x there, you know, we might need to use substitution. So things of that nature. So try and make it look like that. And then we had 2 others that we really need to know. If I got the integral with respect to x of a squared plus, or x squared plus a squared with respect to x, what is this? We have 1 over a on this, so then a is a constant. So it's 1 over a arc tangent of x over a plus c. Okay? So pretty simple deal. Instead of rewriting, I'm just going to go back. What if I had x squared plus 9. Well, let me use a 4. Let me use a 4. Okay, well, that's 2 squared, right? So this is going to be 1/2 arctangent of x over 2 plus c. Okay, pretty simple deal. And then we also have it for the arcsecant. So for the arcsecant, we have antiderivative of 1 over x times the square root of x squared minus a squared with respect to x. So they just, you can either dx out here and 1 over that, or the dx on top, doesn't really matter. But anyway, this is going to be 1 over a arcsecant x over a plus c. Now, those are really the only 3 that you need to know here, because the other ones, are just a minus sign of that. Arc cosecant antiderivative, I'd have a minus sign over here. So this is equivalent to minus 1 over a arc cosecant. Or if I had a minus sign here, I could just put same thing here with arc cosecant. So just changing this real quick, what if I had dx over x times x squared minus 16. Well, square root of 16 is 4 squared, so it's 1/4 arcsecant x over 4 plus c. I could also say that's equivalent to minus 1/4 arc cosecant of x over 4 plus c, right? So it's equivalent to the arc cosecant version with a minus sign. So hopefully that helps out. Just a real simple, quick one. If I wanted to do, let's just do integral with respect to x of square root of 4 minus 9x squared. Well, in this case, I want to rewrite it, right? So this is integral with respect to x. So 4 is 2 squared, right? That's my a. And then 9x squared, I can rewrite as 3x quantity squared. So it's pretty close, to the arc sine one, but what I got to do here is that is a function of x. That's not just an x. So I got to let u equal 3x and du equals 3 dx. So dx is going to be replaced by du over 3. So that's 1/3 can come out front, integral du, and then what I got, square root of 2 squared minus u squared. Now remember, this one is arc sine. So arc sine, so the 1/3 still there, but then the arc sine doesn't have the 1 over a, which in this case 1 over 2 doesn't have it. So it's arc sine u over 2 and then plus c. And then of course, then we back substitute. So instead of u, we're going to rewrite that as 3x. So it'd be 1/3 arc sine 3x over 2 plus c. Okay, so hopefully I'm good. Hopefully you are. Yeah, last minute questions. I'll give you a minute on that. I'm gonna stop recording though.